Okay, let's review Chapter 7 by looking at some old test problems. That is over the power method and Newton's method for systems. And here's one. It says use the inverse power method to find the smallest eigenvalue of A. And it gives you A inverse, so you don't actually have to calculate A inverse. In fact, it doesn't even tell you what A is. So if the power method finds the largest eigenvalue and absolute value, if you want the smallest one, that is the closest to p equals 0, you take the inverse of A minus 0I, in other words, A inverse. So if you just want the smallest one, just find the largest eigenvalue of A inverse, because the eigenvalues of A are the inverses of the eigenvalues of A inverse. So you find the largest eigenvalue of A inverse using the normal power method, and the smallest eigenvalue of A will be 1 over that. So you simply, it tells you what to start with. Start with 1, 10, 1, and do 3 iterations. That is, just multiply by A inverse each time. And comparing this to that, this is about 20 times, this is about 19 times that, 20 times 19, well, they're all 3 components are almost very close to 20 times that, so the largest eigenvalue of this matrix is 20, therefore the smallest eigenvalue of A is 1 over 20. And here's a typical 7.3 problem. Solve this system using Newton's method. Just need to remember what Newton's method is. It's very much like Newton's method for single equation, except instead of 1 over F prime, you have the inverse of the Jacobian matrix. And it says starting from 0, 0, so you plug in 0, 0 into F and Y, and you get minus 1 and 1. That's F of 0, 0, G of 0, 0. Now the partial derivatives, partial of F with respect to X is 4X, partial of F with respect to Y is 1, partial of G with respect to X is minus 2, partial with respect to Y is 2Y, and you plug in X and Y equal to 0, so you get this. And you could just use Cramer's rule to take the inverse of that, and you get this times minus 1, and you get that. Now, whether that's closer to the true root or not, I have no idea, but it doesn't matter. It just said do 1 iteration, just so you know the mechanics of Newton's method. Here's another power method problem. At this time, it's not to find the smallest, just find the largest eigenvalue, so just the normal power method. And just start with 1, 1, 1 if you don't have a better idea, and multiply by A 3 times, and approximately x3 is about 4 times x2, therefore 4 is an eigenvalue. It's the largest eigenvalue of A, and either one of these is eigenvector, so it asks for the corresponding eigenvector. So if you say this, that's correct. If you say that, that's close to correct also. I divided through by the 43, and you get approximately 1, 2, 1. Just multiply or divide by any non-zero number, and it's still an eigenvector. And the largest eigenvalue is about 4. This is actually the same matrix that we did in my example in the last in the 7.2 videos. The largest eigenvalue is 4 indeed. And then the next is another Newton's method problem. You just you have to take everything on one side, and F is x squared plus xy cubed minus 9 plus 3y and so forth. G is that minus 4x minus 2x. And starting from 0, 0, you plug in 0, 0 into the F and G, and you get minus 9 minus 4. Partial derivatives, partial derivative of F, remember F is x squared plus xy cubed plus 3y minus 9 is equals 0. So derivative with respect to x is 2x plus y cubed. Remember, the derivative with respect to x means consider y to be a constant, so that's just a constant times x. The derivative of a constant times x is the constant y cubed. Derivative of x squared is 2x, and derivative of 3y is 0. Then the derivative with respect to y, that's a constant, so that's 0. That's a constant times y cubed, so it's 3xy squared. And then you have plus 3y, derivative of 3y is 3. So, when you take the derivative with respect to x, just consider y to be a constant. Take the derivative with respect to y, consider x to be a constant. Then you plug in x and y equals 0, and you get this matrix, and have to take the inverse of that times that, and there's the answer. Okay, this time you want the smallest eigenvalue of this matrix, and they didn't give you the inverse, so you have to calculate it yourself. And it's rigged so that the inverse has all integers, and it says to start with 3, 8 because it converges faster that way. Multiply by a inverse twice, and it's already pretty much converged. Each of these components is about -6 times that. So the largest eigenvalue of a inverse, see, we just applied the power method to a inverse. Largest eigenvalue of a inverse is -6. Therefore, the smallest eigenvalue of the original a is -1/6. Two more typical test problems from 7.2 and 7.3. They're all kind of similar. 7.2 is just a different matrix, and you take about 4 iterations and find the largest eigenvalue and the corresponding eigenvector. You can, if you just say that's the eigenvector, you'll get full credit. If you say that's the eigenvector, you get full credit. If you divide this through by 5760, like I did here, and say that's the eigenvector, you'll get full credit. Now, this one's a little bit different in that this happens to be a linear problem. So it says start from 1, 1. So here's your xn, yn minus. Now the Jacobian would be 1, 1, 2, 1. Inverse times, plug in 1 for x and y here, and you get 5 and 3. And actually it says do 2 iterations. So after 1 iteration, you get 3 minus 6. Now you go back and plug that in, and you see you get F1 and F2 are both exactly 0 because it's already converged. So after another iteration, it's still 3 minus 6. So after 1 iteration, it's converged exactly, and it wouldn't matter what you started with. You'd get the exact answer, and the next step, it wouldn't change because it's linear. So just like, well, because Newton's method is based on approximating F1 and F2 by their tangent planes, and if the functions are already planes, then their tangent planes are exact approximation. It looks like the 7.2 problems are all pretty much alike. You either find the largest eigenvalue by applying A directly, largest eigenvalue of A directly, power method, or smallest eigenvalue by applying the power method to A inverse and taking 1 over it. And Newton's method typically just take 1 or 2 iterations just so you confirm that you understand it. So most of the others are pretty much the same, but this one is a little bit different in that it's a little harder. It's not just polynomials, so it takes a little more work to take the partial derivatives. So here's your F and there's your G. You're starting from 0, 0, so you plug in x equals 0, y equals 0, and you get 1 plus 3 is 4. Sine of 0 is 0, sine log of 1 is 0, so you get 4, 0. Now the partial derivatives, the derivative of this with respect to x, that's x plus 1 to the 1/2 power, so the derivative is 1/2 x plus 1 to the minus 1/2. Derivative of xy with respect to x is the constant y. Derivative with respect to y, that's constant, so it's 0. Derivative of constant times y is the constant x. Derivative with respect to x here is cosine of x plus 2y times derivative of x plus 2y, which is 1. Derivative of that is 1 over 1 plus x times 1. Derivative with respect to y, use the chain rule here. Derivative is cosine of x plus 2y times derivative of x plus 2y, which is 2. Because remember, y is the variable, x is constant, and log of 1 plus x is just a fancy constant when you're taking the derivative with respect to y, so that derivative of that is 0. Then you plug in x and y equal to 0 into all of this, and you get this diagonal matrix, which is easy to find the inverse of. And there's 1 iteration. And the rest of the Chapter 7 problems are almost the same as what we've already seen, except this one's a little bit different. It says do 1 iteration of Newton's method starting from 0, 0, 0. This is a system of 4 equations and 4 unknowns. And, well, starting from 0, 0, 0, 0, so there's a 0, 0, 0, 0 vector there, minus the Jacobian times, well, you plug in all zeros and you get 0, minus 1, 0, 0. Now, the Jacobian, well, first function with respect to x1, Okay, so the Jacobian matrix, well, see, this is part C, so you have to go back. That would be way too much work to actually find the Jacobian and take the inverse, but it's all the hard work's done for you in the previous problem. See, it says this matrix, it gives you the inverse. Well, this matrix happens to be exactly the Jacobian of that matrix, so you already have the inverse, and this is the inverse. So the Jacobian has like 0, 1, 1, 1, 1, 1, 0, 0, and so forth, but this is the inverse, so it would certainly be an unreasonable problem if I hadn't given you the inverse of the Jacobian, so you just have to multiply that inverse, which is given for you, times that.